Hello, everyone. Welcome back to the Green Chemistry Education webinar series hosted by the Green Chemistry Commitment and Beyond Benign. My name is Amy Cannon. I'm the Executive Director and Co-Founder of Beyond Benign, a nonprofit organization dedicated to green chemistry education in K-12 through higher ed. This webinar series is designed to highlight relevant topics in green chemistry education for faculty and students who are looking to adopt green chemistry in their courses and programs. As a reminder, we're broadcasting live and recording this session, so all attendees are in listen-only mode and all lines are muted. If you have a question, then please type it at any time during the webinar into the chat box, the question chat box there on your control panel for the moderators to view, and we will respond to as many questions as we can at the conclusion of the presentation. So the recording is posted on the link that you see in the welcome box there, the second link that we just sent there, that's the correct one, and also on this PowerPoint slide. Any supporting documents, so such as the PowerPoint presentation slides, will also be posted on that link as well. For those of you who participate in social media, please feel free to connect with us on Twitter or Facebook. We'd love to, as always, hear some live tweeting going on. So please join in if you like. And thanks so much for joining us and taking part in this discussion. The webinar is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming chemistry education, expanding the community of green chemistry practitioners, and growing departmental resources for those looking to adopt green chemistry. The program is a voluntary, flexible program for adopting green chemistry student learning objectives in your own way and for promoting the work that you're currently doing at your institution that can serve as models for others to adopt green chemistry. You can find more information on our website and the link at the bottom of the slide, or feel free to email us, myself, Amy, or Derrick Ward directly as well. As part of the webinar series, we always give away a green chemistry book at the conclusion of the webinar, so we'll be randomly announcing a winner from our list of attendees at the end of the webinar, and we will send a book directly to you. So look out for an email if you are the winner. So for today, we're very happy to have Derrick Ward right here from Beyond Benign and Erika Daley from My Green Lab join us for a discussion about a new resource guide that we're launching jointly for the Organic Chemistry Lab course. So I'm going to introduce them both briefly, and then I'm going to hand the controls over to them for the presentation. Derrick graduated with a Master of Science in Green Chemistry from Chatham University in 2016. Derrick has a green synthetic chemistry background where his previous work at the US EPA focused on the use of novel mechanochemical flow reactor technologies to enhance chemical transformations. He believes in chemistry that strives to be smarter, more effective, and environmentally conscious. Derrick's passion for green chemistry education was catalyzed by his role as a teaching assistant in undergraduate chemistry curriculum. And as the program manager at Beyond Benign, Derrick leads the development and dissemination of higher education opportunities that progress the advancements of green chemistry in higher ed. Erika currently manages My Green Lab's program throughout North America, their programs throughout North America. Now living in Southern California, she was born and raised in Nova Scotia, Canada. She completed a Bachelor of Science first-class honors with distinction at Mount Allison University, followed by an NCERC-supported Master of Science in Chemistry at the University of Toronto. At the University of Toronto, she served as co-chair of the Green Chemistry Initiative and as an executive member of the Women in Chemistry group. And with that, I am going to hand the controls over to Derrick and Erika. So Derrick, see if that comes up for you. All right, sorry about that. That should do it. Okay.
All right, thank you, Amy, for the kind introduction. Erika and I are very excited to talk to everyone today who are listening in about our brand new Green Chemistry Guide for Undergraduate Organic Chemistry Labs. So without further ado, let's get started. But before we dive into the presentation, we just want to give the audience just an overview of who we are, what we do, and why we do what we do. And Amy kind of briefly described Beyond Benign, but I'm going to give a little bit more detail. So Beyond Benign is a nonprofit organization that is dedicated to green chemistry education, and that spans all the way from K through 12, all the way into the higher education space. And what we do is we develop and disseminate green chemistry educational resources that are centered around the principles and practices of green chemistry, to empower educators, to empower students, and to empower the community at large to practice sustainability through chemistry. And as part of our higher education, we have the Green Chemistry Commitment, which is a very active vehicle that we use in order to disseminate our green chemistry resources to ultimately envision a world that has chemical building blocks of products that are used every day, that are healthy and safe for humans and the environment.
And thank you, Amy, again for the kind introduction. So My Green Lab is a California-based 501c3 nonprofit organization, and our mission is to build a culture of sustainability through science. In addition to working with Beyond Benign and Millipore Sigma to create the guide that we're launching today, we have 3 other primary programs. The first is our Green Lab certification, which sets data-driven standards for laboratory operations. Through this certification, labs are made aware of their most impactful behaviors and how to minimize this impact, and labs are recertified every 2 years to ensure continuous improvement. We also launched the ACT label, which is an environmental impact factor eco label at the end of last year, and it has been a rapidly growing program ever since. Sustainability data are gathered through the ACT label process, which is then communicated to consumers through the ACT eco label. And this is similar to a nutrition label on food packaging, only this tells you the environmental impact factor of a chemical, consumable, or piece of lab equipment. And this sets a standard to enable procurement departments to establish uniform sustainability guidelines for laboratory products. And finally, we helped found the Center for Energy Efficient Laboratories. And this is a partnership involving the California utility companies and the EPA. And CEAL sets the standards for energy consumption of laboratory equipment and has led to the first Energy Star ratings and utility rebates for lab equipment. And the most recent example of that is ultra-low temperature freezers, which are often referred to as -70 or -80 freezers that now have an Energy Star rating. So you might be wondering what brought us together. This might be a little obvious, but for this particular project, you can see that we both have similar overarching missions and visions for the future. And through our other programs, My Green Lab and Beyond Benign independently identified a strong need for more green chemistry resources customized to higher education. So we took this opportunity to collaborate because we both have unique expertise and programs that complement each other at the intersection of green chemistry in higher education.
And through this collaborative partnership and project, Beyond Benign and My Green Lab are reimagining chemistry education. We understand that in order to make a lasting change, it all starts at the beginning. So through continued efforts of Beyond Benign's K through 12 program, and now the work that we will be discussing in more detail today, we are expanding upon available resources for higher education and colleges and academic institutions in order to train future chemists and innovators and scientists to apply green chemistry principles. And because the reality is that students in colleges and universities are going to become working professionals. And with a solid foundation or understanding of green chemistry and its innovative capabilities, they can then take this into their professional workforce. And whether they become lab chemists, whether they go work for the government, startup, or even the education sector, they are then able to take that information and create products and materials that are going to be innovative, they're going to be benign, they're going to be sustainable, renewable, and efficient. And then through all of this, just by providing green chemistry education materials, we can then cascade into a more overarching theme where then we create a healthy environment and a healthy society.
Okay, so before we jump into the new curriculum guide, we would really like to hear from all of you in the audience. What teaching demonstrations do you most wish that you had a green chemistry alternative to? And this can be for any reason, whether it's a safety concern, the amount of waste generated, a specific chemical that you think should be eliminated, or any other reason. So if you want to go ahead and write in the chat box an example of the demonstration that you would like to see an alternative for, we'll give you a couple minutes to do that. We really appreciate your input here.
Great, I can see some coming in here, guys. I see a nylon synthesis lab. That's a great one. We see extraction with dichloromethane. Oh, we have another nylon. So, or another polymer. So we have a comment about another polymer as well. So definitely polymerization. And we'll see if we've got more coming in at the moment. Ozonolysis, there's another one. All right, and I'll let you guys know if we see any more pop up. I do see a Diels-Alder as well.
Okay, so I think you guys will be excited to know that some of those we actually do have alternatives prepared in the guide. And then other ones, we are looking to do future projects like this. So any ideas or input that you have, we'll definitely be excited to consider for those future projects as well. So thanks for your input there.
Yeah, that was actually some really good input just from initial feedback that came in, because we will have some answers for some of you guys, and then also expand upon and hopefully highlight some experiments that you didn't think about. So now is the main part of the presentation where we're now going to go in and talk about this new guide that Beyond Benign and My Green Lab has come together to develop with the support of Millipore Sigma. And what it does is it evaluates traditional undergraduate chemistry teaching lab experiments and finds greener alternatives that could be integrated into existing curricula for teaching labs. And through our efforts, we have created a guide that has a set of 10 greener alternative experiments. And the great news is that this is a free, it's open access, and it's a customizable guide that faculty and even TAs can use to integrate green chemistry into their organic lab curriculum. This green chemistry guide is the first resource of its kind, and we are really excited to once again be able to make this public today and talk about its advantages and look forward to see the effects that it's going to have in everyone's academic institutions.
See the contents of here. So we guide readers through the H&S assessment criteria and how these were carried out so that everyone can understand how we perform these assessments in the guide and then use this information to do similar assessments in their own lab. We also highlight a number of solvent substitution and reagent and reaction selection guides, explain how green common laboratory techniques, or how to green common laboratory techniques, and also provide an introduction to green chemistry for TAs and provide an explanation of course, the 12 principles of green chemistry.
Yeah, and then the remaining contents of this new guide, again, we'll have the introduction, have green alternatives, and this is just going to give you a kind of an overview of what the rest of the presentation is going to entail and what you can expect to see. So what makes this presentation this guide so different, and the advantages it offers to like chemistry labs, to faculty in the university at whole? It solely relies on this evaluation of an environmental health and safety metrics that is applied to every chemical reaction within the guide. And this guide created a standard of how to actually evaluate experiments. This resource guide offers a detailed qualitative and quantitative metrics analysis that evaluates the effectiveness of both the traditional organic chemistry labs that students often encounter in their second year in college, and it offers the analysis of the alternatives that have been proven to be quantifiable replacements for those traditional organic labs. And more particularly for the qualitative assessment, each reaction is evaluated based upon the green chemistry principles. And when designing this resource guide, and after evaluating every reaction, it was found that of the 12 principles, 6 of the principles proved to be very effective in qualitatively assessing and differentiating the chemical reactions at hand. And these 12 principles that you will see not only in this presentation, but also within the guide, are the principles of less hazardous chemical synthesis, renewable feedstocks, energy efficiency, catalysis, safe solvents, and accident prevention. And I want to go ahead and just provide more details of what these 12 principles actually mean for those of you who are either new to green chemistry or recently heard of green chemistry. So again, I'm just going to do a quick run through of what these actually mean. And so, less hazardous chemical synthesis. This is whenever practical, synthetic methods should be designed to use and generate substances that possess little to no toxicity. For renewable feedstocks, this one's more simplistic and straightforward because it means that a chemical can be derived from a renewable feedstock. And a good example of this is ethanol that is derived from a bio-based feedstock. The third one is the energy efficiency, and this pertains to when a reaction avoids the use of energy when compared to traditional versions. And for example, and actually what you will see in the guide itself and some of the experiments throughout is like grinding 2 reagents at room temperature using more of a mechanical force using a mortar and pestle versus using a traditional reflux procedure. For catalysis, this one is just the use of a catalyst in your reactions opposed to using stoichiometric reagents. And the safer solvents is just substituting a new solvent for a more environmentally benign solvent. And the last one is accident prevention, which is the avoidance of substances that have potential for chemical accidents. And this can include releases, explosions, and fires. So now that we have covered the qualitative assessment, I'm now going to go into actually what the quantitative assessment was used for the resource guide. And the 2 main ways that it was evaluated was the volume of waste calculation, and I will actually describe this one a little bit further in the next slide. And the second one is the environmental health and safety procedures, where we look at the physical hazards, the human health hazards, and the persistence, bioaccumulation, and toxicity criteria for certain chemicals. So for volume of waste, this analysis is based upon the assumption that all solvents, reagents, and products will be transformed into the waste as waste. And for those of you listening, and if you're a second-year student going through organic chemistry right now, or you've taken organic chemistry, or if you're a working professional who has obviously taken organic chemistry, you understand that typically in organic chemistry lab, you synthesize a molecule, you then calculate your yields, then you analyze your compound to see if you got the right compound, and then from there you then properly dispose everything into waste containers in a fume hood, whether, and then it's like labeled containers, so it's like whether it's aqueous waste, hazardous waste, well, more specific, halogenated waste, organic waste. So because of this analysis, everything is being turned into waste. But to reciprocate that, what this allowed us to do in our resource guide was to be able to quantifiably see whether or not greener alternatives had a reduction in waste compared to others in traditional reactions. And so now we're going to be getting into the actual qualitative hazard assessment within the guide itself. And first and foremost, I just want to say that within the qualitative hazard analysis, this illustration that I have on the slide provides an overall framework of the EH&S evaluation process. And typically, EH&S assessments are viewed as qualitative. So through our efforts here at Beyond Benign and my Green Lab, we have attempted to use quantifiable tools and information and data to develop a method that could analyze chemical reactions based solely on their associated hazards. And it's important to note that all reagents in a given chemical synthesis was evaluated and analyzed based upon these three hazard endpoints. So the physical hazard associated with the chemical, the human health hazard associated with the chemical, and the PBT hazard, which in the previous slide I alluded to, which was the persistence, bioaccumulation, and the toxicity of it. And after gathering information and going through a rigorous process of quantifying it, you then was tabulated into an EH&S table. And this is what the EH&S table looks like, that you will see also further along in this presentation, but also which will be continuous throughout the guide itself. And so when you first look at it, it's very simple to read. So you have the chemical name or the reagents that are used within the chemical synthesis, followed by its Aldrich catalog number. Then there's a column for the amount that is used within the chemical reaction itself, or the chemical or the reaction protocol for the lab. And that's a valuable tool for when we calculate the waste and eventually calculate cost as well as, and again, we'll get into more detail with that later on in the presentation. But the most important thing about this table is the EH&S column. And as you can see, there is an EH&S key at the top right hand of the slide. And for each chemical, it has a three box to indicate the hazards associated with it. So the top box will always be the physical hazard. The second box, or the middle box, will be the toxicity or the human health hazard that's associated with it. And then the third box is your persistence, bioaccumulation, and toxicity criteria. And each one of those boxes then subsequently gets assigned a hazard level depending upon whether it's very high all the way down to potentially no data whatsoever. And it's important to note that during this investigation and within potentially when you're evaluating a brand new chemical that potentially comes onto the market, oftentimes it's hard to find data, but because of that, it's a good way to measure also its effectiveness and potentially the unknown hazards that may be associated with it. So this EH&S table is pretty straightforward, but a lot of you may be actually thinking right now, well, how do you actually simplistically put the color codes into the EH&S column, and how do you actually get this EH&S hazard rating in itself. So now I'm going to go into detail about that. So first, this is a flow process of how we actually get to that point. And we have already discussed the hazard endpoints, so the physical, the human, and the PBT hazards. And so the next step in line to understand how we assign these hazards is we have to first identify and obtain all hazard information. And by doing this, we have to essentially do data mining on all publicly available databases or publicly available resources that are available through chemical suppliers. But the next leading question is, what type of information do we need to look for in order to do this assessment? So again, I have the 3 hazard endpoints listed here above, and for the physical hazard, in order to do this analysis, it's broken down into 3 types of sub-indicators of information that has to be found. So the first is flammability of a particular chemical, of that said chemical, the reactivity that's associated with it, and the corrosivity of it. In the human and health hazard part, it all relates to the overall toxicity and its potential for toxicity. And that then breaks down into whether it has acute toxicity or if it has chronic toxicity. And for the persistence, bioaccumulation, and the toxicity hazards, it's based upon the aquatic toxicity, and more specifically, the toxicity to fish. So now that we understand, and I've run through kind of the information that is needed in order to do this assessment, once all available information has been found, the next step is then to analyze and evaluate all the information for that particular chemical or compound using standardized guidelines and ratings. And all these guidelines and ratings can be found on page 11 and 14 through 14 of this resource guide, and I highly recommend everyone going to the guide and taking a more technical and deeper look, as I'm now going to just go through and give more of a simplistic definition of the guidelines that were used, but it gets much more technical, and I again advise everyone to go to pages 11 and 14 of the guide. But I do want to give some information on, okay, what type of guidelines were actually used. So the National Fire Protection Association guidelines and standards were used, and those were particularly for the flammability and for the reactivity for a certain chemical. Also, global harmonized system labels and the information within those were also used for the corrosivity and some other information in order to analyze and evaluate the chemical's toxicity. But also being within, whether it's been academia or if you're a working professional, MSDSs and safety data sheets are another source or one-stop place to find this type of information too. But also, you can find information on databases as well on chemical substances, and a couple of them that we have recommended and uses are the ToxPlanet, the Pharos, and Green Screen for safer chemicals. And then once you have taken and obtained your hazard information, you then analyze it against the standard guidelines that are presented. From those tables and guidelines, then the appropriate designation for the hazard level is then assigned to the chemical and then put into the EH&S table. But now I want to give like a real example of how this is done. So the previous slides were kind of an overview and a flow of how this information is obtained and then ultimately used. But now I'm going to give an EH&S valuation of ethanol. So again, the first step is to identify and obtain all hazard information. So particularly for physical hazards, we have to find all the flammability information, the reactivity information, and the corrosivity the information. But more specifically for the flammability, we're particularly looking for the flash point. And for ethanol, it can be anywhere approximately from 10 to 15 degrees Celsius. For reactivity, we're really looking for the chemical stability of the compound in itself and whether or not it decomposes readily. And for corrosivity, we're looking at the globalized harmonized system, particularly for the skin corrosion rating. And so by looking at all the available data, resources that are out there, and then pulling that information together. For the human health hazards, again, we'll be looking at more of the acute toxicity and the chronic toxicities. And this one gets a little bit more in-depth and more robust because just for the acute toxicity for a particular compound, you have to find the oral LD50, the dermal LD50, and also the LC50 for that particular compound. For the chronic toxicity, it's actually more intensive, and you're going to be looking at the carcinogenicity of it, the mutagenicity, the neurotoxicity, sensitization, all the way down to its ability to be an endocrine disruptor. And then based upon the available information, then those are flagged based upon the hazards, whether it's high, medium, or low. And for the persistence and bioaccumulation and toxicity hazards, we are looking specifically at that information. So the persistence, bioaccumulation, and toxicity. For persistence, we're looking at the water, soil, and sediment half-life of those compounds. We are then looking for bioaccumulation. We're actually looking at the bioaccumulation factor. And for toxicity, we are looking for the aquatic fish CHV value associated to it. And so once all this information for one particular chemical or compound is identified, what you do then is we evaluate that hazard against those standard guidelines. And particularly for ethanol, what you find is that for flammability of ethanol, you have an NFP rating of 3. For reactivity, you have an NFPA rating of 0. And for corrosivity, you have a GHS category of 1B. For human health hazard information, and after going through and identifying information, all the hazards were associated due to oral exposure. And for the PBT hazard values, for the aquatic fish CB value, you get the following value, and then for the bioaccumulation factor, you get the 3.2. So once again, after assessing all this information, then comparing them to our guidelines, what ends up being assigned in terms of a worst case hazard rating, and this is really important to note, because sometimes you will be looking, let's say for the physical hazard in itself, you may have a flammability rating of 4 and maybe a reactivity rating all the way at this high hazard as well. And in our assessment, you then assign the worst case hazard rating or the worst case hazard that can be associated with it. So in this case, flammability was an NFP rating of 3, which according to the guidelines is a high hazard. For the human health hazard, since all hazards were due to oral exposure, they were all limited as moderate hazard. And for the PBT hazard values, because of the bioaccumulation factor 3.2, it was rated a low hazard. So by going through this process, we can then kind of put all the pieces together and then come full circle to then properly identify the proper hazard levels for those 3 blocks for ethanol. And so now that I've discussed the EH&S assessments, I'm now going to pass it on to Erika to discuss all the other resources that are available in our guide.
These EH&S ratings that Derrick just walked us through are so important because safety should always be a top priority. So not only do they increase the transparency of the safety of each reagent and solvent used in the reaction, they also set a standard that you can now use in your own teaching or research lab. So now that we have a full understanding of how the EH&S assessments that were carried out, we're going to explore the other resources included in the guide, followed by a quick case study of a few of the actual experiments. So the solvent substitution resources, the use of safer solvents is oftentimes referred to as the low-hanging fruit for implementing green chemistry principles into traditional organic chemistry experiments. There are many solvent selection guides that have been published within the pharmaceutical sector and that are being used as a basis for guiding the selection of safer solvent choices for chemical reactions, extractions, separations, in both academia and industry. So our guide provides an overview of these solvent guides and provides direction on where to find additional information. And then at the very end here, the compilations are personally my favorite and preferred resources because they actually consider the priorities of each of the previously mentioned guides and look at how that affects the solvent ratings. And so they give a more bias-free and comprehensive rating, in my opinion. And then there are also greener alternatives to organic chemistry reactions that have been really on the rise since the early 2000s. This is when new publications begin to appear that presented easily adoptable options for greener organic chemistry experiments. Similar to the solvent selection guides, we've included resources on reagent and reaction selection to further facilitate the adoption of greener alternatives, including key publications in the literature, the ACS-GCI Reagents Guide, and a highlight from Green Organic Chemistry in Literature and Laboratory by Andy Dix at University of Toronto. We have also included a section detailing simple ways to green common synthetic techniques, and this includes distillations, chromatography, and extractions, because these typically employ hazardous solvents, create massive amounts of waste, and both of these can be minimized. So we go into that a little bit as well. And then, since this guide was created for teaching laboratories, we wanted those on the ground in the labs teaching students to have kind of a Green Chemistry 101 resource in case they may not have been educated on green chemistry themselves. In fact, this was motivated by my own personal experience as a TA in grad school and with the Green Chemistry Initiative that I co-chaired. And while this is titled for TAs, it's really a great resource for anyone that is just being introduced to green chemistry, from faculty to undergraduate students and beyond in really any discipline. And finally, this green chemistry guide would not be complete without the 12 principles of green chemistry. We would like to extend a special thank you to the Green Chemistry Initiative at University of Toronto for allowing us to include their graphic of the 12 principles of green chemistry from their collaboration with Compound Interest. Just a quick note, the GCI also has a YouTube video series for each of the 12 principles of green chemistry, and we highly recommend that you check that out as well. All of these resources, especially the solvent selection guides, reagent and reaction selection resources, and the greener laboratory techniques can be applied in research labs. And we hope these extend well beyond the teaching labs and into research projects in various divisions of science, commerce, and even beyond those. And we would now like to take the opportunity to walk through a couple of experiments from the guide to show you each component and how all of the resources we just talked about were brought together to create experiments that you can start using in your teaching lab today.
So one of the experiments that you will see within the guide is alcohol dehydration. And most undergraduate organic chemistry labs study the preparation of alkenes doing this type of dehydration. And for this particular reaction that we have, cyclohexanol that's going to then uses an acid, which uses a strong acid to then form your cyclohexene. And traditionally, concentrated sulfuric acid or phosphoric acid is used as the catalyst for this reaction. And these concentrated acids are corrosive and causes unnecessary waste. and can be harmful to humans and the environment. So with that in mind, in the guide, we have a greener alternative to an alcohol dehydration. And in this proposed greener method, we have the 2-methylcyclohexanol in the presence of, again, of an acid catalyst to then form your substituted alkenes in your cyclohexene. So you have your major products, which is tri-substituted, and then your minor product, which is then di-substituted. But the really great, and then you can also see that there's a big similarity between the traditional reaction too, in terms of the initial starting reagent that is used. And in the greener alternative, it eliminates the use of concentrated acids by using a montmorillonite KSF clay as the catalyst. And the clay itself can be more quantifiably seen as like parallel sheets of silicon dioxide and alumina. And what's great about this catalyst is that it is environmentally benign, it's non-toxic, and it's reusable. And through this whole reaction, what we end up finding out is that just by simply substituting the acid catalyst in the reaction, the whole reaction becomes less hazardous. You're using safer solvents, you're using renewable feedstocks, catalysis to safer chemistry, all the way down to waste prevention. And again, as we've mentioned before, as the EH and S tables are a fundamental part of the evaluation process, each starting material was then meticulously evaluated and given its EH and S codes and or hazard levels. And as you can see, just by you can see that there's a general overall decrease in the hazard profile for the greener alternative compared to the traditional alternative. And you can also see a large reduction in the reagents that are used as well. But some of you may be actually looking at those two tables. And if you look at the two acid catalysts that are used in the traditional and in the greener alternative, you can see that they have the same hazard levels associated with. So that brings up a good question. But what's really important to note is that the high toxicity hazard of the KSF clay is solely associated with its inhalation hazard for silicon dioxide. And since due to the reaction protocols that are adopted and used in the reaction, the opportunity for there's a low potential for an inhalation hazard for the KSF clay. So with that, the hazard then can be easily avoided. And for that reason, again, you can see how just the greener alternative from an environmental health and safety standpoint is significantly better. And then if we look at the whole reaction in total, we find that the greener method offers really good improvements compared to the traditional. So it also eliminates toluene and acetone as solvents. As I alluded to in the previous slide, right, we have reduced waste because of the reduction in solvents, and we have a reusable catalyst. And more specifically, if you look at the table, we have a 66% reduction in waste for a lab just by simply substituting the acid catalyst in the reaction. And also, what we like to highlight too is based upon the information, there is a cost decrease associated with the greener alternative, because the greener alternative, if it comes out, if you're on average, your organic chemistry lab is 100 students, comes out to around $47, and then for the traditional, it's $76. And it's important to know that these costs will vary, but it's a good starting guideline for what you can expect to see, because every academic institution may have higher demands or lower demands.
Okay, and I'm so happy that someone said they wish they had an alternative for Diels-Alder reactions, because that's one of the ones that we chose to highlight. So the Diels-Alder reaction remains one of the most important reactions in chemistry for constructing six-membered rings. A Diels-Alder reaction involves the reaction of a 1,3-diene with an alkene as the dienophile, and it's a very common demonstration in undergraduate teaching labs. A traditional Diels-Alder reaction involves a simple diene, such as 1,3-cyclopentadiene and maleic anhydride. The reaction shown here proceeds by thermal decomposition of the cyclopentadiene and is carried out in organic solvents that have high EH&S profiles. And so this greener alternative that we've added to the guide is a Diels-Alder reaction that's performed in water and eliminates the requirement to prepare the starting materials by thermal decomposition that is required in the traditional approach, while still demonstrating the same concept to students as the traditional approach. This greener alternative takes advantage of the hydrophobic effect to increase the reaction rate instead of a thermal driving force for the reaction. And because of this, the reaction can be completed in an hour, even though the reagents are significantly less reactive than the traditional cyclopentadiene and 1,3-butadiene starting materials. And as you can see in the EH&S profile tables here, which are also, as Derrick mentioned, shown for each experiment in the guide, the greener alternative reaction shows a dramatic increase in safety due to less hazardous reagents. And this is exciting, not only because it's safer for the students and the staff and the TAs that are in the lab. This extends well beyond to ordering the reagents and hazards associated with transportation to the institution, but also propagates through disposal to the EH&S and facilities management staff that ultimately have to take care of this waste. And it provides a safer environment really throughout the entire supply chain of chemistry and how it takes place at teaching institutions. And so the greener alternative experiment, as we showed, eliminates the use of hazardous organic solvents, and the reaction is carried out in water as the solvent, which benefits the reaction driving force. And while this greener method experiences an increase in the volume of waste, it is all less hazardous aqueous waste with a substantially lower EH&S hazard profile. And I mean, from this is a perfect example that you can see green chemistry is a continuously evolving system, and it's not perfect, but it makes improvements wherever possible and has a balance of pros and cons. And there's also a slight cost increase of about $17 per 100 students for the greener alternative method, but this is considerably low considering the increased safety of the greener alternative experiment. And now for the moment I am sure you have all been waiting for, and that I've been so excited for the past, I would say, year. Please visit the Green Chemistry page on the My Green Lab website or follow the direct link here to download your copy of the guide. We have it available in Microsoft Word and PDF formats there. They're both available for your free download. We hope to continue creating resources like this, but to do so, we really need metrics on the impact they're having. Before downloading it, you're first going to be directed to a page to provide your name, email, and institution. We really appreciate you taking a moment to complete your information, as it will make future projects like this possible. Your email is going to be kept confidential. We will not share it with any other organizations. We will contact you once in the future to inquire about your experience with the guide and ask if you need any support. And if we release any new versions, we'll just send you a quick note to update you on that. But other than that, that's absolutely it that we will use your email for. Also, if you implement any of these experiments, if you're using the resource guide in your lab, if you're using the information for any other purpose, or if you have technical difficulties, if you have questions or comments, we would greatly appreciate if you dropped us a note on our contact page through the Beyond Benign website or through a direct email, info@mygreenlab.org, to help us further gauge the impact of this guide. So thank you everyone so much for listening.
Wonderful. Thank you so much, Erika, and thank you, Derrick. That was a really great presentation. We've been this has been actually great while you guys have been talking. I don't know if you've noticed in the chat box, we've had several questions coming in that I've been trying to answer here. So, but I can pull up some just to share with you guys. So if anyone's having a look at your control panel, and you can see in the chat box some of the answers, the questions that we've been answering. We've had some questions about solvents, which, I think that's a really common one, often a low-hanging fruit. There was a question about extractions, and then another one on chromatography, and any suggestions on approaches or alternatives for chromatography. I don't know if you guys had any additional comments on that to add to that. And I can tell you what I pointed them to. I pointed them to
I know some.
Yeah, go ahead.
Yeah, so within the guide itself, there is a section on solvent substitutions for chromatography. So I would just really, tell the individual who asked that question, just go ahead and download that form, because it gives a pretty good, thorough idea of what type of solvents can be substituted for your chromatography needs, but also it gives you all the open for the resource as well that you can direct yourself to even expand further upon that too, and then hopefully that sheds some light into how you can implement that into your research lab.
Right. Okay, great. And I've got a this is an interesting question, comment, and might be for this, for a bigger discussion too, but I'm interested in your take on the statement that for safety liability reasons, all chemistry done in the organic lab should be done in a hood, or industry and graduate program standards for safety have increased over the past decade, and in those environments, virtually all chemistry is done in the hood. We need to follow that lead at PWIs and train our students that the hood is the best place for chemistry, not the bench. So comments, and I guess that's open to either of you guys on that one.
Yeah, so I personally think that chemistry, we should be training undergraduate students especially to be using a fume hood properly, and of course when that's appropriate, but with the high safety standards in grad school and in industry, there are virtually no cases in which you'll find a lab without a fume hood. And so I think, as we've been saying through this whole webinar, we're training the next generation of scientists. And so for them to potentially not have a fume hood or not be familiar with how to use it, I think would be a disservice to that generation. But there are then alternatives and opportunities for which we can have experiments that you don't need a fume hood, but I definitely think they should still be present in labs, and there should be labs that are carried out in the hood to make that distinguishment and show the importance of really doing a safety evaluation before you step into the lab and start doing wet chemistry. And I don't know if you have anything to add to that, Derrick.
No, I think that's, what you said was great. Yeah, because going in, whether a student becomes graduated and they go work in the professional setting, there's always going to be a fume hood there, and they still need to be trained on the appropriate safety measures associated with it. I know you addressed the question pretty well.
Thank you.
Great. Okay, great. And we did have one come in on, I'm curious as to why you chose to use the NFPA rating instead of the GHS category for flammability and reactivity. And I'm happy to address that question too, if you like, because I was involved with much of the hazard information, and understand it's a hazard assessment, right? Not a risk assessment here that we're doing. So that one, it was really most of what we used for the hazard criteria was derived from green screen and some of the other sources that Derrick mentioned as well. The NFPA codes are one of the more recognized ones, so that was one of the reasoning for using those, but they align quite nicely with the GHS categories as well. So they should align, and you essentially get the same hazard profile for the chemical, if that makes sense. And good question. And we just got another question, a couple more coming in here. Is there any information in the guide about industries like Sigma, et cetera, supporting green chemistry products or services? Does that make sense?
Yes, no, it actually does. Yeah, because I know with, especially with like Millipore Sigma, if you go on their website, they actually have lists of what they call greener alternative solvents. I mean, just a whole guide on that alone, and go through the steps and processes to show what you can potentially substitute them with. So whether it's a substitute for dichloromethane, or it's for other chromatography needs, all the way even to doing more biphasic reactions, all the way up to Bruce Lipschitz types of surfactants, and the list keeps going on. Yeah, so again,
Yeah.
you know, I would advise you to be directed in that direction and kind of look at all the available resources that are there.
Yeah, there's a number of examples of things like that. And also I will just point out, as I did mention at the beginning, my Green Lab also just launched something called the ACT label at the end of last year. And so that encompasses greener, or rates, I guess, chemicals, consumables, and products. And so that's also a great resource if you're looking to compare kind of an apples to apples comparison, because it's a standard third-party assessment of these types of lab supplies. And so that's another resource for people looking to address sustainability in lab on things that they're purchasing.
That's a great point. Great comments that have come in. And I have one that I'm not sure if you've come across this, Erika. It's more related to fume hoods in some of your more broader lab sustainability work, but can low air exposure risks of a class experiment be tied to ventilation rates, and whether a filtered hood would be adequate? And then I guess then you could, you know, assess the savings sort of within that. Does that make sense?
Yeah, I think there's a lot of discussion around ventilation rates and doing hazard assessments around those. And I think that is something that is going to have to be left up to the individual institution and any engineers that they work with, and decisions that they make internally, because there's not really a blanket statement for each institution that you could say, okay, yes, everyone can go ahead and put filters on their fume hoods if you just take away this one thing. Because I mean, between industry and academia, people are doing such different types of chemistry and using, I mean, there's millions of chemicals out there that people are using. So I think that's potential for certain institutions, but I definitely, and there is, of course, energy savings associated with reducing ventilation rates, and there are sensors available that can do assessments on and link those to a computer and change the ventilation rates as the contaminants in the air increase and things like that. But that is a really massive project and really massive undertaking that I think would be best left to each institution, and we're happy to make kind of guide that or provide resources, but we definitely can't make a blanket statement that says, yes, that would work for everyone, or no, that would not. I think that takes a lot of work and background information and data collection before you can really dive into a project like that. Okay,
great. And this is probably a good last question. Have any of these experiments been included in the curriculum yet, and how have they been taken by students? I guess we probably have some folks on the call that are muted that could probably chime in on this or on the webinar.
Yeah, so I guess today is the first day of the launch, and that the guide is publicly available. So it's not been implemented. The examples that we ran through are in the guide, but the guide is just being launched today. And so if anyone is implementing those this afternoon in your teaching lab, we would absolutely love to hear from you. But at the moment, I will say for today, no, they have not been implemented in any labs directly as a result of the outreach of this guide.
Thank you. Yeah, and we had a list of faculty that we worked with on this that are actively implementing these. So yes, so we have a good, there's a good number of people who have already started to implement these. Okay, with that, I think I will close. We're past the hour, so just wanted to say thank you to everybody. And the winner of our Green Chemistry Resource Guide is Susan Light. Hopefully I'm saying your name right, so you'll receive an email. And thank you again so much to Derrick and Erika for all your work on this too. Again, please do contact us, reach out to us with any comments, questions as you look over the guide, and we'd love to hear from you. So thank you so much.